Hi, this is Sabir again. In this tutorial, I'm going to make you understand, or I'm going to discuss all about the principal stress and principal axis. So today's lecture is all about principal stress and principal axis. So the principal stress and principal axis, those are very important. The, the broad two terms here in stress tensor, because these principal stress and principal axis are essentially required, especially in geodynamics, especially in mechanical engineering, because these principal stresses are related to any breakdown or any on a fracture development or something like that. So principal stress are really essential to understand any kind of mechanism that occur in material science and geodynamics or geophysics. So that's why I think principal stress are very essential or very important for you to understand if you are interested about all about the application of mechanical engineering or geodynamics or lithospheric stress or tectonic stresses. So it will be really helpful for you to understand this type of stresses. Okay. So what are the principal stresses? Okay. So we have already know from the previous my lecture tensor lectures that for any real symmetric tensor, yeah, stress tensor is a real symmetric tensor. Stress tensor is a real symmetric tensor. Is a real symmetric tensor. Real, right? Yeah, symmetric tensor. And we know that from the tensor lectures, we have already known that for any real symmetric tensor, there exist at least three mutually perpendicular directions, right? And these directions can be determined from the eigenvectors of any tensor, right? So eigenvector of, so if T is an tensor, then there is an eigenvector T, V1, say V2 and V3, and we can find out at least three eigenvectors of any tensor that are mutually perpendicular to each other, right? Yeah. So the planes having this direction, so we know this is a vector, right? So if these are mutually perpendicular to each other, then it will develop three mutual perpendicular planes, right? And having uh, three mutually perpendicular planes, and on this plane the stress vector on this plane stress vector normal to the plane, and where there will be no shearing stresses on these planes are called shearing stress, right? Yeah. And so I'm repeating again. So on this plane the stress vector is normal to the plane. So stress vector normal to that three mutually perpendicular planes where there will be no shearing stress are called the principal stresses. Okay. So for example here, if it is a three-dimensional case, I'm going to make you understand about that. Say it's a cube, so we have three mutually perpendicular planes. For example, say this one, I'm going to change the color. It'll be helpful, yeah. So we will say we have this axis, and we have another axis, and we have another axis. So we have three mutual. So we have plane one, this plane, right? And we have another plane, plane two, and we have another plane here. So we have three mutual perpendicular planes. So there will be a stress vector normal to the plane here, normal to the plane, and along this the normal to the plane, and along this normal to the plane, right? So this this stress vector, this stress vector where there will be no shearing stresses, only this stress, only the normal stress, right? So this normal stress is called the principal stress. So I'm going to make you understand. So principal stress tensor are written generally here. Say for example here, T is a tensor, say sigma 1 1, sigma 1 2, sigma 1 3, and sigma uh, 2 1, sigma 2 2, sigma 2 3, and sigma 3 1, sigma 3 2, sigma 3 3, right? So if it is a tensor, then there will be three stress, those are perpendicular to that, to the three mutually perpendicular planes from that eigenvectors. Okay, so it's principal stress tensor generally written here. Say T is a tensor, and principal stress tensor of the principal stress tensor is that sigma 1 0 0, because all the other stress vectors, all shearing stress are 0. So 0 sigma 2 and 0 0 sigma 0 and sigma 3, right here. So these are the principal stresses here, right? Yeah, and along this axis the direction is called the principal direction. So principal direction must have to have must have to be a perpendicular to each other, right? Yeah, so I'm going to give you an example or how we can calculate or how we can do that. So we can calculate this principal stress generally are written sigma 1 sigma 2 and sigma 3, and we can calculate sigma 1 sigma 2 and sigma 3 from the eigenvalues, and the direction can be determined from the eigenvectors. So we can determine that. So for example, we know um, say for example we have a we know this um, say we have a tensor T here, right? And the characteristic equation of this tensor is we know um, determinant of T minus lambda I is equal to 0, right? So determinant of that. So from there we can find alpha cube minus alpha square I1 plus alpha I2 alpha yeah, alpha I2 and minus uh, alpha I3 is equal to 0. So you know these are the third invariance, second invariance of any tensor, yeah, and I1 is the first invariance of that. So from there we can find out this three roots. From there we'll find three roots, right? So alpha 1, alpha 2, as it is a polynomial equation and power is 3, so we'll have three roots, alpha 2, alpha 2 and alpha 3, right? And this alpha 1, alpha 2 and alpha 3 are principal stresses, you know. So how we can determine, let's see how we can determine from there. We can determine, and the corresponding eigenvectors will give us the principal stress direction. How we can find out? Let's see. For example, we have a tensor here. Say we have a tensor T equal to minus 10, 15, minus 25. Any tensor at any point. Say here. So 15, 20, minus 35, it's 25. It is 25. Yeah. So minus 25 minus 35 and minus 30. Say for example here it is our any stress tensor at any particular point. So from there you can find out this characteristic equation, right? So characteristic equation from there determine T minus alpha and I. So I is identity matrix, alpha is eigenvalue. So it's a three-dimensional cases. So we will have three corresponding alpha 1, alpha 2 and alpha 3. So the invariance of, and I have already calculated some invariance of that. So invariant of I1 equal to minus 20. You know what is the invariant and how to calculate this, right? Yeah. So second invariant is 2575, and invariance, third invariance is determinant of that. So 38750. So from the invariance we can find out this alpha 1, alpha 2 and alpha 3, right? So our characteristic equation would be alpha cube plus the uh, alpha square 20, because this minus and there will be minus, so it's positive, yeah. So minus 2575, right, minus 2575 alpha, yeah. So minus 38750 is equal to 0. So you can if you solve this equation, then we'll have three roots. So alpha 1 is equal to 48.8867. So I have already calculated this, so you can calculate this. Alpha 2 minus 14.6016, and alpha 3 is minus 54 and 2 5 2. So these are the principal stresses. Yeah. So these are the principal stresses in case if their corresponding eigenvectors are mutually perpendicular to each other, right? So if we can prove that their corresponding eigenvectors are mutually perpendicular to each other, then we can say, well, these are the principal stress, and those directions are principal directions, right? So we have to calculate the principal direction. So for principal directions, I'm going to give you an example in case of two dimension, because three dimension is much more complicated and it will take a lot of time. So if you understand the two dimensional, definitely you can understand the three dimensional case as well. So I'm going to give you an example from the Peter M. Shearer Introduction to Seismology, and so from there I would love to give you an example of that. So this book is Introduction to Seismology, and that is from the Peter M. Shearer. This book is second edition, Introduction to Seismology, second edition, and writer is that Peter M. Shearer, who is from the university, who is the professor at the University of California, San Diego, seismology professor. So I'm going to give you an example from his book. So for example, here we have a tensor t minus 40 minus 10 minus 10. So we have a tensor here, right? Minus 60. So we have a two-dimensional tensor, right? And from there we can find out alpha 1, alpha 2, and alpha 3, right? So we can find characteristic equations here, determinant. So minus 40 minus alpha, right? Yeah, minus 10, and minus 10 minus 60 minus alpha is equal to 0. So from there we'll get a characteristic equation. So this is the characteristic equation: alpha square plus 100 lambda plus 2300. Yeah, maybe I forgot. And so from there we can get alpha 1 equal to minus 64.14, right? And alpha 2 is equal to minus 35.86. Alpha 2 minus 35.86. So these are the principal steps we say. So if we have to prove that the corresponding eigenvectors are mutually perpendicular to each other, if those are mutually perpendicular to each other, then we can say that, yeah, alpha 1 and alpha 2 are the principal stresses. So from the definition of eigenvalues or eigenvectors, we know that for any tensor we can find it again. Say if we t is the tensor, then we can find out its eigenvector, say v equal to lambda v, right? So we know that. So we can write down this equation: tv minus lambda v is equal to 0. So we can find out this t minus lambda v is equal to 0. So we can write down here t minus I lambda, because identity matrix transformation with the is the same. So yeah. So from there, right? So we can find out. So we have two eigenvectors here, right? So changing the color. We have the eigenvalues alpha 1 and alpha 2, right? Yes. So for alpha 1 we have to find out the eigenvectors, and for alpha 2 we have to find out the corresponding eigenvalues. So we can find out this for alpha 1 we can find out, for alpha 1, say alpha 1 equal to minus 64.14. So for alpha 1 we are going to find out the eigenvectors. So what is the eigenvector? So we can, so if we replace or substitute the alpha 1 here, then from this, so we can find out this corresponding the eigenvectors 24. Say we know, right? So how we can find out this 24? So what are our vectors here? So t minus say minus 40 minus 10 minus 10 and minus 60, right? So this minus so what is our alpha 1? Alpha 1 is 64.14 times 1001, right? And the whole thing times vector is equal to sorry So it's vector, so this vector is equal to 0, right? So this vector is this vector, and alpha is alpha, so sorry, identity matrix, and alpha is here, so this should be plus, right? Because you have minus and minus this. So if you calculate this, then you'll find this kind of equation here. So v is here v1 and v2, right? Yeah, because we have x-axis and y-axis, so this here v1 and v2. Yeah, so what is this? So if you calculate this, then you can find it 24.14 minus 10, minus 10, 4.14 to v1 and v2 is equal to 0. So if you normalize to the unit vectors, then we will find this um, v1 step 1 corresponding to for eigenvalue 1, right? And v2 1, so corresponding to 1 is equal to, so we find here 0.3827, here 0.9239, so we get that. So what does this mean? This just means these the x-axis unit vectors and this y-axis unit vectors, something like that. So we can if we draw because we normalize this to unit vectors, so if we draw this here, then we can find we draw Cartesian coordinates here, right? So this corresponding to x-axis, and this is corresponding to y-axis. So what is our x-axis? So I'm going to change the color, it will be better for you. So say for example it is 1, and same it is 1, right? Yeah. So 0.38, so it's so narrow here. Say for example here is x, and 0.9 sub 3, yeah, 0.38, so 0.38 should be here, 0.38 and so on, and 9 to say 9 here, 9. So our corresponding vector is here, right? So this is our vector, which is v1 1 comma v2 1, right, sir? And we have to find out another vector for eigenvalues alpha 2 that is mutual perpendicular. If that vector for corresponding to eigenvalue is something like that, then we can prove that, yeah, alpha 1 alpha 2. So you have to find out another vector that is perpendicular, that is something like that. So for example, so we have to calculate for alpha 2 equal to 0 point, sorry, minus 35.86, because we know what is the alpha 2, right? Here alpha 2 is minus 35 point, here minus 35.86, right? So for the alpha 2 we have to calculate the eigenvector. So for alpha 2 we can calculate this way, same way, minus 4.14 minus 10 minus 20 minus 20 is where to be, yeah, minus 20 point, what is that, minus 20.14, same way. So b1 and b2 say is 2 for alpha 2 and 2 for alpha 2, yeah. So it's equal to 0. So from there we can find out b1 b2 is 2 for alpha 2 alpha 2, yeah. So we've got corresponding eigenvectors is minus 0.9239, and here again 0.3827, right? Yeah. So let's draw its position vector. Let's draw its position vector. So its x-axis is minus 92. Say if it is 1, then you see 92, that means here, right? And it's minus 38, so it's here, so something like that here. So this vector is like that. So you've got our eigenvector 1 for eigenvalues for eigenvectors for corresponding eigenvalue 1 this direction, right? And the eigenvectors corresponding to eigenvalue 2 is this. So these are almost perpendicular to each other. So these are almost perpendicular to each other, right? So we can find out this even from the cross product. So from the cross product we know that we can find out this vector, these vectors and these vectors, cross product of that. So if you say it is x and it is a y, so cross product is so you can find out I'm sure the cross product is 0 because the cross product should be 0. So this times this times this, right, plus this times this. So this times this plus this times this equal to 0. So divided by something would be 0. So cross product is 0. So if cross product is 0, then cos theta should be 0. So theta is 90 degree, right? So we have already seen that the corresponding eigenvectors are mutually perpendicular to each other. So in case for three-dimensional case, we can also prove that the mutually perpendicular vectors have three eigenvalues whom we can say these are principal stresses. So I hope you have understood what is the principal stress and the corresponding principal axis and the directions as well. So thank you very much for being with us, and do not forget to subscribe with Sabbir Foundation, because Sabbir Foundation is here to make a series of scientific lectures for you guys freely available. So because Sabbir Foundation believes that if we share our knowledge, it will never decrease, rather than it will increase our enlightenment, and it will increase the light and of that. So thank you for being with us, and do not forget to subscribe with me. Thank you very much, and I'm going to see you on next lecture.